Section 1.1, types of reasoning. In this section, we're going to learn two different types of reasoning, inductive reasoning versus deductive reasoning. When we use inductive reasoning, we're sort of making an educated guess. We're using specific cases or examples to try to reach a general conclusion. When we use deductive reasoning, we know for certain that we are correct. We're using rules that are already established and trying to apply them to a specific case. So those are the two different types of things we're going to look at in this section. Most of what we will be doing will fall in this category, inductive reasoning, although we will touch on this a little bit also, the deductive reasoning. So again, deductive reasoning is using what you know to be true in general. These are things that have been established and we know they are already true and we apply them to a specific case. Um, some people call this top-down reasoning. Inductive reasoning is using observations of specific cases or examples to try to reach a general principle. Some people call this bottom-up reasoning. Let's look at this example here. Predict the next number in the list. So if I asked you to make a prediction on what number would come next in this list, um, it's kind of hard to say. We don't have much to work with, right? We only have 2, 6. How do we know what comes next? I think if you were to try to think about what might come next, you could probably come up with at least, 2 different answers, maybe more, right? I think some people would probably say, well, what kind of a pattern is happening here? We don't know what the pattern is for sure. In fact, we might not even have a great idea because we don't have much to go on, right? There's only 2 examples or 2 cases that we're looking at. I think some people may say maybe 10 should come next, because maybe the pattern that's trying to be established is that we're adding 4 each time. I think some other people may say maybe 18 should come next, because 2 times 3 is 6 and 6 times 3 is 18. Um, Maybe we're multiplying by 3. Kind of hard to say. It's very hard to say. We just don't have much to go on, right? We don't have much to work with right now. So I'm going to kind of hold off on the answer to this. In fact, we don't really know what the answer to this is. Maybe there's even a third or, more like patterns that might be happening that we're just not seeing yet. But sometimes usually I would say we have a lot more to work with. Like, for example, this example down here. If I asked you to predict the next number in this list, I would say most of us could be very certain. I got to be careful though. We're not certain. We're not 100% certain, but most of us would be pretty sure that we do know the next number in this list. Most of us would say, I think we are adding 4 each time. Look at 2 plus 4 is 6, 6 plus 4 is 10, 10 plus 4 is 14. And that pattern keeps happening. And I have several examples to go on. 1, 2, 3, 4, 5, 6. I have 7 numbers in that list. And so I'm fairly sure that probably the next number would be 30. I'm fairly sure that we are adding 4 each time, and that's probably the pattern. And we believe the next number would be 26 plus 4, right? Which is 30. Are we 100% sure? I mean, no, because we don't know for sure what the rule is, but we're close to that, right? We're quite sure, but not 100% sure because we're using what's called inductive reasoning right now. We are looking at specific examples, specific numbers, and trying to guess at what the pattern probably is. So that's what we meant when we said inductive reasoning is sort of like making an educated guess. We are using inductive reasoning at the moment. Okay. So with inductive reasoning, there's always this shadow of a doubt. Like, I think it's 30, but maybe there's some other pattern going on behind the scenes that's not adding 4, it's something else, but would also happen to give these first few numbers. I doubt it, but there's always that small possibility when we're using inductive reasoning. Next example. Let's predict the next number in this list. So we have 6, 8, 12, 18, 26, 36, 48. So what's happening on this one? Let me pause for a few seconds and see if you can come up with the next number. In fact, it might be a good idea for you to pause this video and see if you can come up with the next number in this list. And I'll just proceed here. So what's the pattern happening right now? I mean, it looks like maybe we're getting bigger, so maybe we're adding something or multiplying by something. But it looks more difficult than the previous question we just did. I mean, let's see if we can talk about adding here. I mean, we do add 2 to get from 6 to 8, right? 6 plus 2 is 8. But I don't add 2 right here, so it's not like we're adding 2 every time. Hmm. But what am I adding? I'm adding 4 right here, right? 8 plus 4 is 12. What am I adding here? 12 plus 6 would give me 18. So maybe I'm adding something, but maybe that thing that I'm adding is not consistent. Maybe it's changing because 18 plus 8 would give me 26. And 26 plus 10 would give me 36. So maybe it's the thing that's adding, there's a pattern going on in the thing that's being added, right? 2, 4, 6, 8, 10. 12 would come next, and that makes sense. 36 plus 12 is 48. So it looks like we found a pattern having to do with adding, but not adding the same number each time. The thing that's adding is being changed and following a pattern itself. And so I guess if we believe this, that we should continue this, we should add 14 to 48. And I believe that would give an answer of 62. 14 plus 48, 62. So that was a little more difficult than the one before. You never know what it could be. It could be add, it could be subtract, it could be multiply, it could be divide, it could be something else. It could be a lot of different things going on. Anything is fair game with these pattern problems. How about the next example? Predict the number in this list. Um, I guess I think it's a good idea in general when you're watching these videos for you to pause at this point, pause the video, try to do the problem on your own, and then come back and see how we do it. So I won't be necessarily pausing or giving you time, but you can pause the videos on your own while you're watching. And I think it's a good idea to do that and try it and then come back and see how we do it together here. So in this problem, I don't know what's happening. We're getting bigger, but then we're getting smaller, like 10 to 19. We got bigger, but then 19 to -1. We got way smaller there, but then we got bigger again to 8. Then we got smaller to a negative number. So something strange is happening here. Something's like alternating possibly is what might come to mind here. And let me show you that we actually add 9, of course. 10 plus 9 is 19. But I'm not adding anything here. In fact, I could think of it, maybe I'm subtracting something. Maybe we minus 20. Like 19 take away 20 is definitely -1. But what happens next? How do we get from -1 up to 8? Um, we're adding 9 right there, actually. -1 plus 8, um, or sorry, -1 plus 9. That does get me to 8 there. And so plus 9 minus 20 plus 9, maybe it goes minus 20 again. Is 8 take away 20 -12? Well, it is. If you were to go 8 take away 20 on your calculator, you should see -12. Maybe we found a pattern. Maybe it's add 9, subtract 20, add 9, subtract 20. Does that keep going? I think it does. -12 plus 9. -12 plus 9, that does make -3. That works. -3 subtract 20. Um, that does make -23. I think we've figured out the pattern. I think it alternates right here between add 9 minus 20, add 9 minus 20. I think we figured out that pattern. -23 plus 9. That does make -14. You can see that. So probably if we believe that, we should be subtracting 20 from -14 and we get -34. Um, if we believe that, our answer should be -34, right? That would go in the spot of that question mark right there. Again, are we 100% sure about this? We're never 100% sure when we're using inductive reasoning. I mean, that's what inductive reasoning is all about. But we're pretty sure we're close to 100%, but just it's always this little tiny shadow of a doubt that maybe something else is happening. Um, maybe there's a different pattern that would give the same numbers that we see here, but might give a different number here. I doubt it. I'm fairly sure that we are correct here, but when you're using inductive reasoning, you're never 100% sure. You're always making what we call like an educated guess. We're going to use inductive reasoning on this problem. I'd like us to start by just picking a number. In fact, I think it's a good idea. I would like you to pause the video right now, and I'd like you to go through these steps. I'd like you to pick any random number, multiply it by 6, add 10, divide by 2, subtract 5, and see what you end up with. And what we're going to do is we're going to try to compare the number we started with to the number we end with and see if we can figure out a pattern in that. So go ahead and pause the video and try that. Pick any random number you would like and follow those steps and see what you end up with. And we're going to talk about if we can find some sort of a pattern there. I'm going to go ahead and just pick a random number, say 4, right? So what if I picked 4? If I do 4 times 6, 4 multiplied by 6 is 24. And then if I do 24 plus 10, 24 plus 10 is 34. If I then divide that by 2, so 34 divided by 2 is 17. And then finally, if I then subtract 5, 17 subtract 5 is 12. Okay. So what happened when I started with a 4, I ended up with a 12. Okay. Do I see a pattern in what I started with and what I ended with? I don't know, maybe probably not yet because it's kind of hard. That's kind of hard to tell with just one example, right? Let's do another example. Let me pick a random number. Let's say I want to pick 7. Let's pick the number 7. Okay. If I took 7 and multiplied it by 6, 7 times 6 is 42. Okay. If I took 42 and added 10, 42 plus 10 is 52. If I took 52 and divided by 2, I would get 26. And then finally, 26 subtract 5 is 21. So it looks like when we start with the number 7, we end with the number 21. Do we see a pattern between what we start with and what we end with? Maybe you do. I imagine there's a lot of you that do see a pattern, or you think you see a pattern. Are you certain of it? Would you bet $100 on it? I don't know. I think most of us would want to see more evidence. Most of us would want to go through more examples. So before we try to jump to any conclusions, I mean, we only have two cases here. We should do more. Like how many more? Uh, that's up to you. Like different people will take more evidence until they're convinced. Um, I'm going to do at least one more. Let's take the number 10. What if I started with the number 10? Okay. If I started with the number 10 and I multiplied 10 times 6, I would get 60. Okay. If I then went 60 plus 10, I would get 70. If I then went 70 divided by 2, I would get 35. And finally, 35 minus 5 would give me 30. So it looks like if I start with the number 10, it looks like I end up with the number 30. What's going on? What's the pattern between what I start with and what I finish with, what I end with? I think most of you probably right now could say, well, it looks like we're always getting something that's 3 times what we started with. You see how 4 times 3 equals to 12? See how 7 times 3 equals to 21? You see how 10 times 3 equals to 30? It appears that we're going to end with 3 times whatever we started with. Again, is that for sure? No, like we don't know that for sure. We've only checked 3 numbers. There's infinitely many numbers in the world. And so, just because it worked on these 3 doesn't necessarily mean it's going to work on all the other infinitely many numbers. But it's looking like that's the case. We would lean towards saying, I think we're going to end up with 3 times what we started with. If you want to try a couple more examples on your own, that would be great. But at this point, I think we could say maybe it's true, or at least we're using inductive reasoning here. So it's always an educated guess. But it looks like um, probably the ending number is 3 times the starting number. It looks like the ending number is 3 times the starting number. Again, probably. We're not going to bet our life on it right now. We've only checked 3 cases, but it's appearing that way. So that's how inductive reasoning goes. You look at specific examples and you try to form a general conclusion based off of the evidence that you're seeing. Let's, for the first time, look at what we would call deductive reasoning. And deductive reasoning is, remember, when you use deductive reasoning, we are going to know 100% that we are correct. If we can successfully go through this using what we call deductive reasoning, there will not be any wiggle room. There will not be any guessing anymore. We will be completely certain that we are correct. So how can we do that? How can we be completely certain? I mean, really the only way to be completely certain is to check all the numbers in the world. How can we check all the numbers in the world? There's too many. There's infinitely many. I've only checked 3 of them so far. It would take infinitely many days to finish this if I were to try to check all infinitely many numbers. Seems impossible, right? Well, in algebra, we sometimes are able to just give a placeholder that represents any number you want it to be. In fact, in algebra, we often write x, and you say, what is x? Well, x at this point could be anything. X could be whatever number you want it to be. X is a variable. Let's see what happens if I go through this using x. Again, keep in mind, x could represent any number in the world, any number you want it to represent. What happens when I multiply x by 6? In algebra, when I go x times 6, we call that 6x. That's how we write that. What happens when I add 10 to that? In algebra, we call that 6x plus 10. What happens when I divide that by 2? Let's be careful here. When I take 6x plus 10 and I divide that by 2, that 2 actually gets applied to both of those. In fact, it looks kind of like this. And so it's actually 6x divided by 2 plus 10 divided by 2. So we end up with 3x plus 5 when we do that. And then finally, it says to subtract 5. So we have 3x plus 5, but then it says to subtract 5 from that. What happens? Those 5s just cancel each other out, right? And we end up with 3x. I want you to look at what just happened here. Look at what we started with and look at what we ended with. Okay, we started with x. We ended with 3x. I'm very confident now in saying that we will always end up with 3 times what we started with. Because x could represent any number, right? X could represent 4 or 7 or 10 or 12 or 100 or 900 or negative 60 or 3/4 or 5.7. X can be anything. And it looks like algebraically, in fact, we proved algebraically that we'll always end up with 3 times what we started with. Okay. So using deductive reasoning, I now know that the ending number is 3 times the starting number. The ending number is 3 times the starting number. There's no guessing anymore. There's no questioning this. I am 100% confident in saying this now. I am certain about this. So that's the power of deductive reasoning. Deductive reasoning, if you can pull it off, I'm not saying we can do it every time in every case, but this was a good example to show that how deductive reasoning can work. It's much more powerful than inductive reasoning. We're not guessing anymore. We are 100% certain. I would bet any amount of money that we end up with 3 times what we start with because we just showed that right there. We showed it once and for all cases, for all numbers in the world. Okay, let's move on to a different example. This is a true or false question. So it says true or false, and if we're going to say false, we need to give a counter example, which we'll talk about what that means when we get to that. But for all x values, x minus 8 is less than x. For all x values, x minus 8 is less than x. Is that true all the time? Is that always true for all x values? I think we should try some specific x values and just start to see what happens. That's how I think you should approach these problems. Just start to try it with specific examples, specific x values, and see if it's true or false in those cases and go from there. For example, what if I were to pick, say, x equals 10? What would that look like if I plugged 10 in each of those spots? Okay, if I were to put a 10 right there, that would say 10 minus 8, and then less than a 10 right there. So I'm plugging whatever, I just randomly picked this, okay? I'm plugging whatever number I picked in those spots. Is that true or false? Well, 10 minus 8 is 2. Is 2 less than 10? Yeah, of course. All right. So at least this is true when x equals 10. Does that make it true for all x values? No, no, it doesn't. We need more evidence. So we're using inductive reasoning right here. I definitely wouldn't want to jump to any conclusions based off of just one number. Now, if this were false, I would be done already. I would stop. I would say this is false because for this statement to be true, it has to be true for all x values, all of them in the world. So if we can just find one of them where it doesn't work, then we could say it's false. And that x value where it didn't work would be our counterexample. Let's keep going. Let's try x equals 15. Okay, I'm just randomly picking x values here. There's no reason you had to pick 15. If I put a 15 in those two spots, it would look like this. Is that true or false? 15 minus 8 is 7. Is 7 less than 15? Sure it is. I see that it's been true in two cases. That doesn't make it true for all of them. I think we need more evidence. My suggestion is to keep going. Don't just stop after a couple. I mean, I don't want to say there's a specific amount that you need to do, but do more than two for sure. I think what some people do is they only pick like nice counting numbers. When I say counting numbers, I mean like one, two, three, four, five, six type of numbers. Um, and they forget that there's other numbers in the world. There's zero, there's negative numbers, there's fractions, there's decimals. So sometimes people only stick to the counting numbers, but they might find their counterexample if they were to have tried a negative number or a fraction or something like that. And so I suggest you maybe try zero, maybe try negative numbers, maybe try fraction, like try different numbers than just your normal one, two, three, four, five type of numbers. Um, let's try a negative number. I'm just going to make up -3 and just randomly picked an x value because this is all x values. That means it can be any type of number in the world. It doesn't have to be just a counting number. So -3 goes here and here. So -3 take away 8. Is that less than -3? Well, -3 take away 8 is -11. And -11 is less than -3. I realize 11 is bigger than 3, but -11 is less than -3. Some people don't quite get why we're saying that. If you imagine a number line, -11 would be way over here somewhere. -3 would be closer to 0 over there. Whatever number is further to the left is considered the one that's less than the other. So since -11 is further to the left on this number line, it's considered less than -3, which is further to the right. Whichever number is further to the right is considered the greater number. So -3 is considered bigger than -11. -11 is considered less than -3. Okay. I think I said maybe try 0. I put 0 there. That would be -8 less than 0. That's also true on the number line. -8 is to the left of 0 on the number line. So, I mean, it seems like it's going to be true. If you're not convinced, try some more. I believe that the evidence is making us lean towards true here. Okay. Next example. So still true or false. Okay, remember if it's false, we're supposed to come up with a counterexample. For all x values, 3 times x is greater or equal to x. start randomly picking x values. I'm going to say x equals 5. I had no reason for 5 specifically. I just picked a random number. That means I'm going to put 5 in those two spots right there where you see the x. So this would be 3 times 5 greater than or equal to 5. I believe that's true. That says 15 is greater than or equal to 5, which it definitely is. Pick another one. Pick, say, 8. Just made that up, right? Pick a random x value and plug it in both of those spots and see what happens. Is it true or is it false? Remember, if you can find just one where it doesn't work, then we've proved it false because this statement says it has to work for all x values. Is 24 greater than or equal to 8? Yes, it is. That is a true statement. At the moment, we're leaning towards wanting to say true. But remember, don't only check nice whole numbers, like nice counting numbers, 1, 2, 3, 4, 5 type of numbers. Um, Sometimes 0 might give you the counterexample that you're looking for. A negative number might give you that, or a fraction or a decimal might give you that. So don't only check these nice counting numbers. Let's check 0. If I plug a 0 in both of those spots, 3 times 0 greater than or equal to 0. That's actually still true. I know it's equal to itself, but that does say greater than or equal. So 0 is greater than or equal to 0. That is a true statement. Okay. I believe there would be some people who would probably stop right now and say, I've had enough. I'm going to say true, right? You're taking a risk there. Um, we haven't checked, a negative number. We haven't checked fraction or decimal. Like sometimes you will find your counterexample. Sometimes there is no counterexample and true is the correct answer. Sometimes you will find a counterexample if you were to try a negative number. Let me just try a random negative number, x equals -4. If I plug -4 right in both of those spots, for x, it looks like this. 3 times -4 is -12. -4 greater than or equal, I'm sorry, -12 greater than or equal to -4. That is false. -12 is not greater than or equal to -4. Again, remember, if you think about a number line, you got 0 right there. -12 is way over there. -4 is much closer to 0. The number on the far left, the number that's further to the left is considered the lesser number, and the number further to the right is considered the greater number. So -12 is actually less than -4. It's definitely not greater than or equal to it. So that's why we're saying false. So we're saying false, and we are giving a counterexample of x equals -4. When we say counterexample, that's the example that led us to say false. So that's what they mean up here when they say, if you're going to say false, tell me why. That's what they're saying. Give a counterexample, right? That's the x value that led us to say false. That's what they mean by counterexample in this case. Continuing on this true or false direction, the product of any two counting numbers, or this product of any two odd counting numbers is an odd counting number. The product of any two odd counting numbers is an odd counting number. Again, when we say counting number, we mean the numbers that you count with, like 1, 2, 3, 4, 5, and so on. That's what we mean when we say counting number. Okay. Now, I think you also should know what an odd number is, right? That's 1, 3, 5, 7, and so on. Okay. Those are the odd numbers. Even numbers, of course, being 2, 4, 6, 8, 10, and so on. What does product mean? Product means multiply. Again, I think it's a good idea while you're watching these videos, when I introduce a question, pause the video on your own, try to get an answer. You try to figure out if it's true or false. Remember, if you're going to say false, you should provide a counterexample. You should provide why you are saying false. You're going to say, this is the example that I looked at that proved it false. That's the counterexample. Let's just take some random odd numbers and multiply them together and see if the answer is an odd number. That's what the question's asking, right? So, I don't know, 3 and 5. 3 and 5. Those are both odd numbers, right? Those are two odd numbers. Let's take the product. Let's multiply them. 3 times 5. 3 times 5 is 15. 15 is an odd number, right? Odd, odd, odd. So at the moment, or at least for 3 and 5, we would say this is true. 3 and 5 are both odd numbers, and their product became an odd number. When I write x here, this is multiplication. This is not like x like we did earlier today, where it could represent any number. This is 3 times 5. Don't just stop and say the whole thing is true just because it was true in one case. Pick other pairs of odd numbers and multiply them together and see if you get an odd number as a result. 7 and 9. I just made up two other odd numbers. Let's go see what happens when I multiply 7 and 9. 7 times 9 is 63. All of those are odd, right? We took two odd numbers, we multiplied them together, we got an odd number. At the moment, we're still leaning towards true, right? There's nothing that we've seen that would want to make us say false to this statement. Does that mean it's true for sure? Does that mean this statement is true for sure? No, it's only true so far in those two cases that we've seen. We've got to do more. Again, I'm not going to give an exact number of how many you need to do. You need to do enough to convince yourself one way or the other. I mean, if you find just one example where it's false, then go ahead and stop because you've proven that it's not true all the time. Let's do another one. I'm just going to take like 11 and 15. Those are a couple just random odd numbers. If I were to multiply 11 times 15, okay, what do we get? 11 times 15, I'm getting 165, okay, which is odd, right? We started with two odd numbers. We ended up with an odd number. You can try more examples. Like you may not be convinced by only these three examples. I'm going to go ahead and tell you this is a true statement. You are not going to find any counterexamples on this one, but you should definitely, if this was a test question, for example, I would be looking at more, I would want more evidence. I would be looking at more cases than just these three. We're not looking at zero or negative numbers here or fractions or decimals because we're talking about counting numbers. Counting numbers are these like nice numbers that you're used to here. Moving on to our last question of the section, all numbers divisible by 6 are also divisible by 12. All numbers divisible by 6 are also divisible by 12. So what do we mean by divisible by 6? Like 6 times 4 is 24, right? So that means 24 is divisible by 6. Let me check 24, right? So 24 is definitely divisible by 6. 24 is divisible by 6, that means when I divide it, I get a nice answer, a nice whole number answer. That's what we mean by that, right? But 26 is also divisible by 12 because if I divide 24 is also divisible by 12 because if I divide 24 by 12, it also gives a nice whole number answer. So 24 is a number that's divisible by 6, but 24 is also divisible by 12. That would I would lean towards saying true for my final answer based off that one exam, right? But that would be bad idea to stop right now and say true. You might be right, but there might be a counter example. We've only looked at one example. We've only looked at the number 24, which is divisible by 6 and also happened to be divisible by 12. Does that mean every number that's divisible by 6 is also divisible by 12? Not necessarily. Try another one. Let's try, say, 60. 60 is definitely divisible by 6, right? Because if I take 60 and divide it by 6, I get a nice whole number answer. That's what we mean when we say divisible by 6. Is 60 divisible by 12? I think it is actually. 60 divided by 12 also gives me a nice whole number answer. Okay, so 60 is divisible by 12. So that specific case is true. Again, that doesn't mean necessarily that this whole statement is true all the time. It just happened to be true in those two cases that we looked at, 24 and 60. Okay? I would really caution you not to stop right now and say true. You need more evidence. You need to look at more numbers that are divisible by 6 and see if they are also divisible by 12. Because if you keep doing that, I think you're going to find a counterexample. Let me give you a counterexample. Look at 18. 18 is divisible by 6. 18 divided by 6 gives you a nice answer, right? Nice whole number answer. That means 18 is divisible by 6. Is 18 divisible by 12? I don't think it is. If you take 18 divided by 12, that's not going to give you a nice number answer. If you take 18 divided by 12, it gives you a decimal answer. It's not a whole number, it's 1.5. If you're getting a decimal number there, that means it's not working, right? It means it's not divisible by that. That means 18 is not divisible by 12 because we didn't get a nice whole number answer there. Okay? So that is false. And as soon as you find one counter example, you're done. Like you can stop. My counter example is 18. All numbers divisible by 6 are also divisible by 12? No, they are not. Because we came up with a counter example that showed it's not true all the time. So that's what we mean by these true false questions. If you're going to say true, then just say true. You should be pretty sure of it by have you had checked a lot of cases. If you're going to say false, you can say false as soon as you find one time where it doesn't work. And that is called your counter example. Thank you for watching. That wraps up section 1.1, types of reasoning.